Aristides Baldodano, pediatra intensivista, presidente de ACANAMED. Al doctor Cohen Van Besien, profesor invitado. Sea bienvenido aquí al Colegio de Médicos y Cirujanos y a Costa Rica. Director del programa de trasplante de células madre en la Universidad de Cornell, USA. Doctor Amita Wikema, profesor invitado, hemato-oncólogo, director del Laboratorio de Terapia de Células Madre, Universidad de Chicago. Doctor Juan Cruz, PhD, Universidad de Buenos Aires, Argentina. Doctor William Buján, hematólogo, Universidad de Costa Rica, coordinador del Foro. Colegas, médicos, profesionales en salud, señoras y señores. De verdad, muy buenos días. Y empezamos con que recordemos que este año el Colegio de Médicos y Cirujanos cumple 160 años de fundado. Se inició como protomedicato, fundado en aquella época por el doctor Juan Rafael Mora Porras, en relación a la necesidad de regular la medicina, promocionar la medicina, y de verdad, como consecuencia de la epidemia del cólera de 1856, después de la guerra contra los filibusteros. Pasa posteriormente el Colegio de Médicos en 1895 a formarse o llamarse la Facultad de Medicina y Farmacia, que así se mantiene y rige la medicina hasta 1940, cuando a través de la ley 362, el doctor Rafael Ángel Calderón Guardia crea la Universidad de Costa Rica y por lo tanto el nombre de facultad se necesitaba para una facultad en el futuro de medicina, la cual se abre en 1961. Y por lo tanto el colegio adquiere su nombre y se le da también pues, su reglamento en ese momento. Nuestra ley orgánica data de 1962. En este colegio en este momento estamos sumamente ocupados para tener una nueva ley orgánica. Sin lugar a dudas, el Colegio de Médicos y Cirujanos es una entidad que no debemos olvidar los médicos y todos los costarricenses. Es una entidad de fin público al servicio del país, al servicio de los ciudadanos y al servicio de Costa Rica. Esa es la razón fundamental de todos los colegios profesionales en este país. Está fundado por medio de leyes, para los que no conocen, y la colegiatura a este colegio, o sea, ningún médico puede ejercer la medicina si no está incorporado a este colegio. Eso nos da una serie de ventajas con respecto a otras series de circunstancias a nivel mundial y latinoamericano. Como dijimos, el colegio es una entidad no estatal de fines públicos, que los cumple en representación del Estado y su objetivo supremo es el bien común de los costarricenses. Por lo tanto, la razón de ser de nosotros es existir por el bien de la ciudadanía y de la sociedad. Y para cumplir con nuestro fin, el Colegio de Médicos no solamente debe tener un aspecto gremial, que lo hacemos, que consideramos muy bien, cuidamos de nuestro gremio, pero también en este colegio y en esta junta directiva actual estamos porque cumplamos la labor fundamental que consideramos no lo hemos venido haciendo de la mejor manera en este país. ¿Cómo cumplimos nuestra labor? Uno, garantizar la no práctica ilegal de la medicina, tanto por particulares como profesionales en salud que no son médicos. Dos, que no haya intrusismo, es decir, que el médico que no tiene la capacidad ni la formación haga procedimientos invasivos o no para los cuales no está debidamente acreditados y que no los tengan registrados dentro de su perfil profesional especializado, cosa que en este momento nosotros estamos empeñados en que todos los profesionales incorporados acá, especialistas o especialistas, tengan su perfil para que dentro de ese marco profesional puedan ejercer la profesión y no haya esa situación de intrusismos. Que el ejercicio de la profesión esté totalmente apegado al cumplimiento de nuestro recién actualizado y aprobado Código de Ética. Desear al país que los profesionales que se incorporan como médicos generales, especialistas y subespecialistas tengan la preparación académica y las habilidades adecuadas y correctas que garantizan una práctica de la medicina de óptima calidad profesional, académica y ética. Y 5, garantizar también que los médicos ya incorporados se mantengan al día en su preparación académica, en sus conocimientos, a través de una educación médica continua, pero lo más importante, una recertificación médica obligatoria que podría ser cada 5 años. Esos son nuestros objetivos desde ese punto de vista. Dado eso, ese punto de vista, el Colegio de Médicos y Cirujanos y la Academia Nacional de Medicina ACANAMED, con el fin de cumplir con ese fin fundamental y preocupados, como lo dijo el doctor Aristides, el doctor Buján, porque lo que es la terapia celular, terapia regenerativa, etcétera, hemos visto con gran preocupación que se está haciendo en una forma totalmente no regulada, con una proliferación incontrolada, de alguna manera hasta abusiva en ese tema. Y eso realmente nos preocupa porque de alguna manera también estamos haciendo daño o bien no estamos siendo claros ni transparentes con la población de este país. Y sin lugar a dudas, este tema se las trae. Sabemos muy bien que este tipo de tratamiento, lo que son trasplantes de células madre y lo que se ha dicho terapia celular, la única o prácticamente una de las pocas aplicaciones aprobadas son lo que se utiliza en tratamientos hematológicos. Hay una serie de riesgos cuando se utiliza esta terapia y sin lugar a dudas han surgido una serie de usos en los cuales no hay una evidencia científica adecuada, tanto como lo que es dermatología, cosmetología y otros aspectos importantes. Riesgos asociados a esta terapia: transmisión de enfermedades infectocontagiosas y de enfermedades hereditarias. La célula madre puede madurar en un tipo de célula diferente a la que se tenía por objetivo inicial. Podría implementarse o implantarse esa célula en otro órgano y ahí proceder o provocar un proceso de proliferación y diferenciación, generando tejido ectópico anormal, etcétera. O sea, y desgraciadamente nosotros hemos visto de que no se ha hecho de la mejor manera en este país. Con excepción de las células madre hematopoyéticas, el uso de células de otro origen, incluidas las autólogas de tejido adiposo, se encuentran en fase experimental. Así, todas las intervenciones que utilicen estas células necesariamente tienen un carácter investigativo y deberían normarse bajo la ley reguladora de la investigación bioética 9234 y su reglamento. Leyes que, como lo dijo el doctor Baltodano, de alguna manera les falta consistencia, no cumplen y son débiles en algunos aspectos. O sea, deben utilizarse únicamente, creemos, bajo un proceso y protocolo de investigación que debe ser revisado y aprobado por un comité de ético científico y avalado por un Consejo Nacional de Investigación en Salud, en ese caso el CONIS. Ustedes lo saben muy bien también de que un manejo aquí en Costa Rica de la extracción, del manejo, del cuidado, del proceso de aplicación, que también no es correcto en lugares, no ha habido una adecuada acreditación. Entonces, definitivamente es un tema, como lo decimos ahorita, lo estamos diciendo, que está de alguna manera hasta cierto punto caótico y hay que regularlo, hay que normalizarlo, hay que acreditar los lugares en que se hace desde el punto de vista del profesional, de los profesionales en salud que de ahí trabajan, microbiólogos, etcétera. ¿Qué debe hacer un médico? ¿Qué debe hacer un microbiólogo? ¿Qué debe hacer? Eso hay que regularlo. Y es por eso que el Colegio de Médicos, con muchísimo gusto, se ha unido a ACANAMED en este tema. Tan es así que el colegio ya fundó desde el año pasado una comisión de células madre y lo que es terapia regenerativa, en donde el que ha llevado el peso ha sido el vicepresidente del colegio, que es el doctor Carlos Salazar Vargas, que hoy no nos acompaña porque está fuera del país. Pero en una forma responsable, en una forma coherente con lo que queremos hacer desde el punto de vista de regulación de la profesión, estamos totalmente de acuerdo con traer este tema al tapete y sin lugar a dudas, este foro nos viene a nosotros con invitados realmente extraordinarios, nos va a dar una luz, un camino a seguir en donde a través de nosotros y de colegio podamos insistir con las autoridades para que haya una regulación adecuada y cumplamos y con lo correcto esta terapia a nivel nacional. Así que muy complacidos y bienvenidos al colegio. Gracias.
Muchas gracias, señor presidente. El foro está diseñado en una parte introductoria y nos vamos a ir adentrando hasta terminar en el punto, digámoslo así, álgido, que lo vamos a tener mañana, que son aspectos regulatorios. Hoy vamos a tener charlas que son realmente una gran mayoría básicas, teóricas a su vez, pero que nos van a ayudar a ir conociendo cómo es este asunto de la medicina regenerativa. Gran placer de nuevo de presentar a un amigo y que no es la primera vez que viene a Costa Rica, ya ha venido por lo menos unas 5 o 6 veces a Costa Rica. Nos ha ayudado mucho en la parte de hematología y a tratar de ordenarnos durante ya muchos años. Nos conocimos hace ya más de 20 años, 25 años, siempre rodeados de un tema y que ha sido el tema de la célula madre. El doctor Kun Biesim, que lo conocí en el MD Anderson, posteriormente él pasó por la Universidad de Illinois, luego Universidad de Chicago y actualmente es director de la unidad de trasplante del Hospital Presbiteriano de Nueva York, que pertenece a la Universidad de Cornell. Comenzar a nombrar que ha sido el doctor Van Biesim a nivel de hematología en Estados Unidos y a nivel internacional me va a llevar mucho tiempo. Ha sido múltiples veces presidente de comités de investigación, tiene más de 250 publicaciones y es una persona, un gran experto a nivel mundial en tema de trasplante y de células madre. Inmediatamente que yo le pedí que me viniera a hablar sobre célula madre, me dijo, yo no sé mucho de eso. Y yo le dije, si usted no sabe mucho, ¿quién va a saber? Pero dichosamente me aceptó la invitación. Por favor, Kun nos va a explicar qué es la célula madre en sí. Okay. This is the point. You move here.
Okay. Thank you. So, gracias, Willem, y gracias, señor presidente, para invitarme. Como lo entiendes, yo hablo un poco español, pero eso es un tema muy, muy, muy complicado. Entonces, si no sé, prefiero al menos empezar un poco en inglés. Es más fácil para mí para explicar. Entonces, what are stem cells? It's a complicated issue. By definition, is he translating? Yes, he's translating. The definition of a stem cell is a cell that can self-renew and that can also give rise to cells of multiple lineages. So how do I explain this? Oh, sorry. F5 probably, right? Okay. How do I explain this? A stem cell is a cell that can renew itself. So if it's a hematopoietic stem cell, it can give rise to another hematopoietic stem cell. And do I have a pointer here? This is the pointer. So it starts as a stem cell, and it can turn cell. That is self-renewal capacity. But a stem cell can also give rise to a cell that is more mature. A hematopoietic stem cell can give rise to a myeloid progenitor or a lymphoid progenitor, and then that progenitor itself can divide again into an erythroid, red blood cell progenitor, a white blood cell progenitor, or a megakaryocyte. So that is the definition of a stem cell, a cell that can give rise. Sorry, I do something wrong here. a cell that can give rise to itself. It can self-renew, auto-renovation, but it can also divide in an asymmetric fashion. I apologize. In an asymmetric fashion, it can become different types of cells, and it can give rise to cells of multiple lineages. Now, a stem cell can be a very primordial stem cell, an embryonic stem cell, the cell that gives rise to all of us, but it can also be a cell that arises from a more differentiated tissue. Stem cell, there can be a bone marrow stem cell that gives rise to hematopoietic cells, there can be a mesenchymal stem cell, and I will talk briefly about all of these cell types. Others will talk more about their applications and about what we can do therapeutically with them. I will give only very brief examples. I will try to introduce you to the topic here. So I divided the talk into 4 different categories. There are embryonic stem cells, iPS cells, which I don't know how to translate in Spanish, induced pluripotent stem cells, and perhaps a little bit different category are the cells that are derived from cord blood that we typically think of as hematopoietic progenitors, but that may be a little bit more complicated. So what are embryonic stem cells? Células madres embrionarias. They are derived from the inner cell mass of a blastocyst. So this is a 1-day or 2-day-old embryo, and one can pick out the cells from the inner cell mass that in nature will give rise to a human being or to a mouse or whatever origin it is derived from. And one can, for the last 20 years, put these cells in colonies and grow them in a dish and derive various organs or progenitors of various tissues from this. This is a very powerful discovery. Obviously, to me, as almost as a doctor or as a biologist, it makes sense that this cell exists. We clearly all derive from an embryonic stem cell. But the fact that this cell can be cultured in a colony and then be manipulated to give rise to various tissues, that it can be genetically manipulated, gives both great excitement and opens all our eyes to great potential for regenerative medicine, because in principle, one can grow anything from that. One could grow nervous tissue, one could grow muscle, one could grow blood. At least in principle, one could do this. One also is concerned about the ethical implications. What can one not do that could have unimaginable consequences? And this concept of embryonic stem cell colonies give rise to a lot of debate during the Bush presidency, as I recall, in the United States. I was already in the United States at that time. This is a very controversial cell, and there are many ethical problems or questions, depending on what side of the debate you are on. And its use has been somewhat restricted, and even its research has been somewhat restricted. So how do we get around this? How can we create a cell that is similar to the embryonic stem cell, but that does not have the same ethical problems? There were a number of attempts, and you may remember Dolly the sheep. A lot of you will remember Dolly the sheep. And Dolly the sheep was derived from an egg cell, an oocyte, where the nucleus had been removed and another nucleus of another sheep implanted, and that gave rise. Sorry, they took the nucleus from adult tissue of a sheep and they implanted it into an oocyte, an egg cell, of which the nucleus had been removed. So they took the cell nucleus with the genetic information from one animal and implanted it into the environment of an egg cell that gave rise to the adult animal. And that worked, but never was much advanced. And about 10 years ago, so this, going back a little bit, this embryonic stem cell could give rise to pretty much every cell in the body. About 10 years ago, the concept, a group in Japan, Dr. Takahashi and Yamanaka, and Dr. Yamanaka subsequently received the Nobel Prize for his discovery, discovered that we could recreate an embryonic stem cell from an adult cell. One could take, I believe, in their initial experiment, it was a fibroblast, therefore an adult cell, and by genetically manipulating this cell in a rather simple fashion, they knocked in 4 genes. The genes were called OCT4, SOX2, KLF4, and c-MYC. The most famous one in my mind is c-MYC of all these genes. All these genes are involved in early differentiation of embryonic cells. When they put these genes in an adult cell, then the adult cell acquired the properties of an embryonic cell. So they could de-differentiate an adult cell back into an embryonic cell, not a real embryonic cell that came from could come from a red blood cell progenitor, could come from a skin cell, could come from a fibroblast, and they could give it back these pluripotential properties. That was then called an induced pluripotent stem cell. And that really has revolutionized the field, because obviously there are no ethical problems with taking a cell from the skin or a cell from adipose tissue or a cell from any organ and reprogramming it and giving it back these primordial characteristics, these properties that allow it to de-differentiate into an undifferentiated cell and then re-differentiate under our command, let's say, into a cell that has specific properties. So imagine somebody who had a sarcoma and had an amputation of the bone, and it's a young child, and you have problems with bone growth for the rest of his life. In principle, at least, you could take cells from that person's skin, de-differentiate them into induced pluripotent stem cells, and grow bone. You could take somebody who had a car accident and had spinal cord injury, take cells from the red blood cells, de-differentiate them, and grow them back into neuronal stem cells and cause the healing of the nervous system. And I truly believe that's where we are going. But I think we are 10 years away from that, at least. And others will talk about that in much more detail. So, but that is where all the excitement comes from. So the principle is established. The practice is far from established. And I hope that others will talk about that much more. A lot of people are working on achieving these goals. And I will just give you one quick example of a recent publication where macular degeneration of the eye, a disease of the elderly, where cells of the retina degenerate, where they took cells from the fibroblasts of an elderly lady, they reprogrammed them with these 4 factors, induced them into induced pluripotent stem cells, re-implanted them, and this led to improvement in eye function. And I think this will be repeated again. This is the first, to my knowledge, practical example of clinical use of induced pluripotent stem cells. Now, that is fantastic. Keep in mind also the eye is an organ that is protected from the immune system. It's the easiest organ to do any type of genetic manipulation from and to change tissues in. And I believe they treated only one patient. And so therefore, this is very early days. All the other applications are years away, and this was done in a very careful fashion. But I think this is the future. Now, perhaps easier, let's take adult stem cells. What are adult stem cells? Adult stem cells are tissue restricted. They are multipotent, they are not pluripotent, meaning that they can give rise to their progeny. A hematopoietic stem cell can give rise to myeloid cells, megakaryocytes, red blood cells, but it cannot go back and cause brain tissue, or it cannot go back and create bone tissue, at least not in principle. The dogma is it cannot, unless we transfect it and make iPS cells, which is technically still very, very difficult. There are other stem cells. Every organ turns out to have stem cells. This concept really derives from hematopoietic stem cell transplant, where it has been known for many, many years, and we routinely transplant these cells for bone marrow transplant and for curing leukemia. But in the last 10 years, there's an explosion of knowledge on other types of stem cells. Gastrointestinal stem cells were found in the bottom of the crypts of the gastrointestinal stem cell, of the gastrointestinal system. Mast stem cells exist. Pancreatic island, and perhaps some Dr. Wickrama will talk a little bit about that. Mesenchymal stem cells. In principle, there are stem cells for every purpose. Other than using them for bone marrow transplant, hematopoietic stem cells, and a little bit for pancreatic islet transplant, I am not aware of that many applications, but others will talk about that. But there's a big question here. Is this dogma true that adult stem cells cannot differentiate in other tissues? And there's for a long time been a question, can stem cells, adult stem cells, convert into another type of stem cell? Plant world, this is not uncommon. One can put a leaf of a plant, some trees in the soil, and grow a totally new tree of it from it. So in a plant, a cell can differentiate and redifferentiate fairly easily. Does this happen with adult stem cells? And there have been long, intriguing observations. For example, in bone marrow transplant, we find like a year later in a patient, we do a skin biopsy, and we see in the skin some cells that look surprisingly as if they were of donor origin. And the way we see that is by sex mismatching. We have transplanted a male with his sister, and all the hematopoietic cells are from the female. However, once in a while, you come across reports where it is mentioned, listen, we found a cell in the skin and it looks like a true skin cell and it is of donor origin. So perhaps under the right circumstances, an adult stem cell can convert back into a cell of another tissue, be it to a limited degree or be it to an extensive degree. And that's, I think, where a lot of enthusiasm comes from, but also where a lot of the misuse comes from that was already mentioned. Because if that were the case, and we could do that reliably, then it would be very easy to grow new organs. It would be very easy to repair the spinal cord, because we would take bone marrow stem cells, very easy to obtain. We've done it for 30 years. We would inject them in the spinal cord and the spinal cord would heal. The problem is it's not so easy. And even though questions there continue to linger and a certain amount of conversion may be possible, it is probably extremely limited. And again, perhaps others will talk about that. But perhaps the most studies have been done in heart disease. And some of you may remember, these are already old studies I'm showing here. When preparing this talk, I thought back about the old days. And if you look back to the early 2000s, there were a lot of trials of injecting hematopoietic progenitors, what we call CD34 selected stem cells, either into the bloodstream or into the coronary arteries of people with a myocardial infarction, with the idea that we would hasten healing of the myocardium. And this is a paper in Nature, a very prestigious journal, I would say, of a mouse model where they injected GFP modified hematopoietic stem cells in a mouse that had an artificially induced myocardial infarction. So they ligated coronary artery. The mouse had a thinned myocardial wall, like it should happen if you have a myocardial infarction. The myocardial wall becomes fibrotic and becomes thin. And they injected hematopoietic stem cells into the bloodstream. Hematopoietic stem cells were stained green. They were GFP, green fluorescent protein. And as you see, they show up in this infarcted area. So they are attracted to this infarcted area. And at least in this model, this is an animal model, mind you, this is not humans, but in this model, they hastened healing of the myocardial infarction. So there was a lot of enthusiasm about this. We are going to treat myocardial infarctions with hematopoietic stem cells. And there were at least 5 trials. And some of them were in the New England Journal of Medicine, and the results are inconclusive. So it's not totally nonsensical. It makes some sense. There may be something there. But if there's a capacity for reconversion and for healing other tissues, it is quite limited and may not be clinically applicable and may not have clinical use. And at least for myocardial infarction, I don't think we are doing any studies any longer. 10 years ago, I remember that I was working with Dr. Wickram. I remember that we talked to our cardiologist, should we initiate studies about this? But that field, although initially with a lot of promise, seems to have failed. Now, that has not stopped people from doing this. And there's a lot of studies, a lot of clinics around the world where people take cells from any tissue and tell their patients, we are going to inject it in another tissue, and your dementia will get better, your eyes will get better, your walking will get better. And that is the problem. This is published in the New England Journal of Medicine in 2017, I believe. And this was a clinic in Miami, Florida, where people were taking, where patients came with macular degeneration. And instead of this careful study that I showed you a couple minutes ago, where one patient was treated in a very complicated fashion, no, they took adipose tissue. They took adipose tissue from the patients and they did something to it, whatever it was, and they injected it in their eye. And there were 3 patients who were treated in this private clinic, and they then came to the University of Miami when they went blind. And so this, the University of Miami published this as a warning, and only then did the FDA crack down on these on this clinic, and this clinic is closed, I believe. But so this type of approach is what is the big concern about regenerative medicine. And the last quick point that I want to make, if adult stem cells can convert, a lot of people are putting a lot of hope in using umbilical cord blood stem cells. So We collect routinely umbilical cord blood at birth in a number of centers, and these umbilical cords contain hematopoietic stem cells. Adults have the hematopoietic stem cells only in the bone marrow. Newborns have them in their blood. And it makes sense that these cells, they are just newborn. They are literally a day old, or they have just had intrauterine life. They have very different immunologic and hematopoietic properties. They have to last as a lifetime, not another 10 or 20 years. And they are, at least in hematopoietic transplant, they have fascinating characteristics. A lot of people believe that they may have better characteristics of conversion into other tissues than adult stem cells. And they have been used in studies of cerebral palsy, where kids are born with cerebral palsy and get an injection of umbilical cord blood stem cells, spine repair, diabetes mellitus. Just from a review in the Transplant Journal this month, the number of patients treated on such studies is up to 800. The number of indications, neurological, diabetes, cardiac, and vascular, a number of studies. But the conclusion, once again, is these are studies. There's nothing established. There's some hint that this may work in cerebral palsy and alleviate cerebral palsy, but it is very, very early days in that respect. So at the end, and I borrowed a lot of these slides from one of my colleagues at Cornell, a PhD researcher who is interested in stem cells, Dr. Todd Evans, who I should acknowledge. And this was the last slide he gave me. And these are his words. Very few stem cell treatments are proven safe and effective. And I think we'll end up talking a lot about this the next couple of days. Clinics peddling unproven stem cell treatments frequently overstate the benefits and use patient testimonials to support their claims. An experimental treatment you pay for is not the same as a clinical trial. Cells from our own body are not necessarily safe as a treatment. That's also the statement of some of these clinics. You no longer need donor cells. We take your own cells. But if they are manipulated or if they are injected into an organ where they don't belong, they're not necessarily safe. They are less supervised by the FDA. They are less regulated. That is for sure. Park Avenue stem cell as at the front. This is from an ad. It doesn't come through very much, but it talks about Park Avenue stem cell is at the forefront of regenerative medicine. Really. So with that, I thank you for listening to me, and I will be happy to answer any questions.
Muchas gracias, Kun. Escriban por ahí las preguntas y luego el doctor Amita, vamos a sentarnos y a plantearle las preguntas. Otro de los placeres que he tenido recientemente, gracias a una colaboración que hemos mantenido con la Universidad de Chicago y vía Kun y otros amigos, es tener hoy la posibilidad de contar con el doctor Amita Wikrema. Él ha dedicado muchos años en este tema, gran especialista a nivel en Estados Unidos, tanto así que cuenta a nivel de la Universidad de Chicago con un laboratorio dedicado a terapia celular y con múltiples publicaciones en el tema, con un amplio conocimiento también sobre lo que es la parte regulatoria, y es una de las personas que está más inmersa en este charco, digámoslo así, que es de la medicina regenerativa. Lo invité y muy gustoso me aceptó la invitación, y por acá lo tenemos para que nos hable en este primer tópico, que es realmente ayudarnos a definir qué es terapia celular, medicina regenerativa, tipos de células, ambientes, etcétera, etcétera. Doctor Ramita, por favor. Sí.
Oh, perfect.
Right.
Okay.
Right. No, no. Okay. This is the point.
Oh, okay.
And this is
Up and down. Yeah, I can also use.
right.
Okay, thank you. Thank you so much for inviting me. Actually, I met Willem last night for the first time, although he's been to my university many times. And actually, it's my first trip to Costa Rica from Sri Lanka. It reminds so much like Sri Lanka, tropical environment. So thank you. And I'm going to actually build up on my colleague Kuhn's basic introduction. And it's going to be a little different. I'm going to give you some aspects of regenerative medicine that's more practical, what's being done in the world right now, especially in the United States and in Europe. And so some of the couple of first slides are just the introduction of stem cells, actually beyond the blood stem cells. And then I'll talk about the FDA. Many of you may not be aware. So the regulatory body in the United States that regulate all clinical medicine is Federal Food and Drug Administration, FDA. So any clinical trial to actual approving standard of therapy has to go through the FDA. So I'm going to give a separate talk on the regulation, but I'll show you some of the therapies that involve stem cells that's been already under clinical trials, or very few that's been approved in the United States. And then also I'll talk about the two types of stem cells that are being now coming into treating patients. One's based on iPS and also embryonic stem cells. And the type of stem cells that actually is really taken off in the last 5 years is based on mesenchymal stem cells. Actually, this seems to alleviate many of the problems that the blood stem cells have, and it's just beginning to take off. So I'll talk about some of the introduction. So I'm showing this slide because we all think regenerative medicine is new. If you go to Greek mythology, they talk about regeneration of liver. So essentially, many things we think that are really new that we are discovering, it's already there. It's just we have to discover them. Same thing with regeneration. Many of you are aware salamanders can regenerate their limbs. So there are possibilities. Human species are one of the few that cannot regenerate. Why is it? So those are some of the secrets that we still need to uncover. So essentially, if talked about this regeneration, we should probably be able to discover ways to come up with methods to regenerate our cells that have been damaged. Stem cells itself. So this is very, very more fundamental than what even Kuhn had mentioned. So of course, we have embryonic stem cell, which is the most primitive stem cell that's in an embryo. And again, like my colleague mentioned, characterized by these transcription factors that define it to be a stem cell. Actually, this is the part that's taken a lot of interest in the last 5-7 years. I'm doing the same problem. I'm going to use this. There's a lot of interest in the fetal stem cells, and the fetal stem cells can come from, not from the embryo itself, actually, from amniotic fluid, water and jelly stem cells, which I'll talk quite a bit about. So the water and jelly stem cells are from the cord itself, isolated from the cord itself. Also placenta and amniotic membrane itself. So these cells have become a good source of starting material for regenerative medicine. And one of the key reasons is because of a lack of an immunogenicity. So cannot be rejected. And then less potential is this adult stem cell. And of course, the progenitor cells do not have the regenerative capacity. It's already decided to go into a particular lineage, like Kuhn had mentioned, to a red blood cells or a myeloid cell. So most of the focus is on these types of cells and also the stem cells themselves. And so how do we find out whether we have stem cells? So I'm just showing you one slide. This is actually was done. It's a very old slide from my lab itself. So this is a blood stem cell. So how we recognize that there is a stem cell, if you take a bone marrow aspirate or a blood, is there a stem cell? How many stem cells are there? So we figured out a way to do in vitro assays to recognize stem cells. So typically what we look for this type of an assay, it's called cobblestone area forming cells. If you put in a dish with the stromal cells, if you do have stem cells, what happens is they form a really tight refractile group of cells. Those are extremely primitive stem cells. For example, these two both have stem cells. These are all stem cells, but this is no stem cells, just regular blood cells. You do not have those refractile tight cells. So this is a way you could actually begin to understand whether your bone marrow, for example, has stem cells that can be used to treat a patient. So here, this is non-blood stem cells. Again, like Kuhn had mentioned, this is an undifferentiated embryonic stem cell, but then they form these embryonic bodies. So what's happening in terms of clinical applications is people retrieve these, isolate these cells in vitro in the lab, culture them, and manipulate them and prepare a cell dose to give it to patients. So these are some of the clinical trials that are being tested. And then for example, so the part that Kuhn alluded to actually has become the #1 upcoming treatment. The first type of treatment is for macular regeneration. And this is the cells that's been used after manipulating in the cells to be clinically transplanted into patients. So these are some of the basic morphologies of these stem cells that are being used. And of course, you can also get them to become neuronal cells in vitro. So this, I got it from the website from the US regulatory authority. Every treatment that's been approved for standard of therapy, not clinical trial, it's gone through clinical trials and now it's become standard of therapy, is published. So you can see only these, there are actually two others that I didn't put in here, only a handful in terms of cell therapy or regenerative medicine that's approved right now in the United States. So of course the cord blood cells for transplantation is approved. When I say approved, what it goes through a step called licensing. After phase 1, phase 2, phase 3 clinical trial, if you want to commercialize it, in other words, you want to charge a patient money and do the treatment, you have to get a license. So cord blood is licensed now. The other common thing of these approved is all autologous. The other one that's just been approved is autologous fibroblasts, and this is for treatment of improved appearance of wrinkles. And this is from this company called Fibrocell Technology. Also, this therapy is now approved for repairing cartilage. So these are all different types of progenitors or stem cell tissues that's been in vitro expanded and has been shown to have some improvement or some efficacy. That's why they've been approved. And Provenge, many of you might be aware of Provenge. It's for prostate cancer. It was one of the first cell therapies that were approved now about 7, 8 years ago. And the latest one was last week, actually. This is one of the biggest breakthroughs in cell therapy. This is for cancers. So the first indication for standard of therapy that was approved last week by the FDA is for pediatric ALL. So you take your patient's own T cells and then modify the T cells to recognize the tumors, essentially targeting an antigen called CD19. And then the cells are sent back to the clinic and we infuse. So this went on a what's called accelerated phase. 63 patients were treated, 82% showed remission. That was such a good result. This is now approved. Actually, my institution is the first place in Chicago now that's offering this therapy. On a clinical trial, we treated 4 or 5 patients, and beginning last week, now we offer a standard of therapy. So this is only a handful of patients that's been already, a handful of studies that's been approved by the FDA. So I'm going to go through a couple of list of trials that's been undergoing clinical trials for regenerative medicine purposes. So this is, again, I got it from the FDA website. So whenever any treatment needs to go to clinical trials, you have to apply for an application. So this number that I list here, so that FDA has provided this number. Look at how many, this is just the last few years, it's exploded all around the world for macular degeneration. So these are clinical trials that are either completed or now recruiting. They all originate the cells that are embryonic stem cells or iPS-derived stem cells that's been expanded and manipulated by companies or entities and going through testing for macular degeneration. So if you were to look at several of them are from Japan. Actually, this is from United States, University of California. And then there's a whole host of others right here. Actually, there is one from Brazil that's recruiting for the same thing, but all the sources are embryonic stem cells, but with different flavors. And then also a hospital in China. But these are all US FDA regulated trials that are going through. So I expect this to become a standard of therapy in the next 2 or 3 years, licensed product. And they're all coming from ESCs or iPS cells. The next few slides, actually, I'm going to concentrate on MSCs. They're called mesenchymal stem cells. The reason this type of stem cells have taken on its own kind of life is because MSCs, you can take it off the shelf. It doesn't have to be autologous. They lack immunogenicity. So many MSC trials have shown you can just like giving a pill. You can take a drug from any cells and give it to somebody else and there won't be any rejection. So where do the MSCs come from? Many sources. So this really shows you can isolate MSCs from endometrium, placenta, amniotic fluid. These are the 2 tissues that has really people have been using quite a bit. Umbilical cord itself derived MSCs and also bone marrow. I'll show you now people are realizing there's quite a few drawbacks of using MSCs from bone marrow because many of the trials, I would say in our last 10 years, have used bone marrow as the source, but the results have not been as promising as expected. But more promising results are coming from umbilical cord. And then you can differentiate it into all these types of cells. And so this actually shows the work that's been done from MSCs from all these different tissues. As you can see, this index really shows both research, development, and clinical use. Umbilical cord derived MSCs have really taken off, and of course the bone marrow is there. The other one that's really take a prominent role is adipose tissue, not because it's good, because it's easy to use. What Kuhn had shown that the patient that went blind was used from adipose derived, especially in a lot of Asian countries. They charge you money, they take your own fat cells, they then inject it somewhere else. So there is a term for this by the FDA. It's called non-homologous use of tissue. Use means you take your own cells and put it into somewhere else for another use. In other words, taking bone marrow and put it in the heart is a non-homologous use. Taking bone marrow and put it in the bone marrow is homologous use. So the problems becomes, even using non-homologous use becomes a problem. So this is the issue with using fat, adipose, for regenerative medicine, people have realized. When you take somebody's fat cells, this is what you get. It has a fatty portion, liquid portion, and a cell pellet. So it's defined as stromal vascular fraction, SVF, which contains native fat cells and also liposuction. But if you take this and inject, what are you injecting into these patients? These are all the types of things that you're injecting. So you have adipose, fibroblasts, smooth muscle, endothelium, and blood cells. Also all these progenitors. But the active part, if it works, that truly will make a difference is this compartment right here. This is where the stem cells are. But the problem is when you take this liposuction, only a very, very minor fraction of this is true stem cells. So all the other things can have bad effects. And so using SVF without purifying is a big issue. And that's what's being done in many, many clinics, including trying to treat for wrinkles, to blindness, to other things, and it does not work properly. So a few years ago, this is a position paper that was published by ISCT, really defined what, because people were doing this, a lot of physicians were doing this around the world. So SVF really was defined what they came to an agreement, and then characterization of the population of adipose-derived stromal cells, ASCs, which has the greatest therapeutic potential, still remains unclear. So many of the things that's been done is to try to characterize this a little better. But I think the biggest use for mesenchymal stem cells will come not from the adipose, other types of tissues. So that's what I want to show you the next few slides. So the part that has really taken a lot of attention is MSCs from umbilical cord. And this is also not controversial. When a baby is born, you throw out the placenta, you throw out the umbilical cord. If you were to get the umbilical cord, the inner lining of the umbilical cord is a jelly kind of cells. It's named after its discoverer, Wharton. So it's called Wharton jelly MSCs, which has stem cells. And these are all the clinical trials. This is again in blue. So these are legitimate clinical trials that the FDA has looked at the applications and assigned a name. So these are all the clinical trial numbers. And these are preclinical and clinical trials that's been conducted in the US and around the world, and all for many, many diseases right now. But again, this is not a standard of therapy right now. It looks promising, has a long way to go, but looks like it may work. So many of us are familiar with doing clinical trials using MSCs from bone marrow. This goes back to about 15 years right now. And including my lab actually has a bank of MSCs from bone marrow from a company, whole bank. The purpose is if a nuclear attack comes along, they claim that these MSCs can prevent from bone marrow failure for nuclear radiation. So there are, and graft versus host disease is another indication that the bone marrow MSCs has been used. But it hasn't been as efficacy as we expected. The reasons are these. So if you were to get a very young donor, you have these very, very nice MSCs. These are really nice fibroblast cells. But if you get an older donor, no spindle shape morphology, few mitotic cells. So these types of cells are not very good for regenerative medicine. So that's where many of these original bone marrow stem cells were coming from adults. So, and also donor variability can be an issue. And also they have very differentiation potential. Also, there are lots of subset of stem cells and many different issues. But the other thing is it's also low in numbers. So you have to really grow in vitro and expand them and create a bank and characterize them. So, and also, of course, it's painful to harvest and risk of infection. So people are trying to move away from bone marrow derived MSCs and more concentrate on umbilical cord MSCs. And the other reason being, like I mentioned, there is no problem with rejection, immunogenicity. So if we were to get a brand new baby's umbilical cord and create a really well characterized bank, it's not controversial, non-immunogenic, and it's very, very naive in terms of recognizing self from non-self. And so just to give you a quick anatomy lesson here, where these stem cells are coming from. So the umbilical cord itself can be isolated from them. So many of the cell therapy facilities in the United States are accredited by Foundation for Accreditation of Cell Therapy. FACT. Actually, now it's become a worldwide organization. And I am an inspector. I inspect banks around the world. And lately, I have inspected several in Asia. Many of the cord blood banks that collect cord blood to save it for your baby to be used in the future now also give the families an option to save the piece of the cord. So some banks don't have the technology, they will save the cord. Others actually digest the cord, isolate the MSCs, and in couple of vials, cryopreserve. In the future, they can create a bank out of it. So, and that area is just becoming more standard of therapy, not therapy, but collecting, and just like the cord blood banks, collecting cord blood cells. And then also has both the yolk sac and also placenta also has cord blood. I mean, also has stem cells that you can save. So human water and jelly stem cells seems to be the one that's taking off in terms of doing many, many more clinical trials. So I'm going to go through a couple of major characteristics of these cells. Why it's good? Again, it do not express HLA-DR. Also, some of these markers, but also do not secrete, also secrete prostaglandin E2. In other words, it suppresses the immune system. So these are good characteristics to have, and also inhibit differentiation and maturation of dendritic cells, thus no inflammatory reaction. So this is how these cells look like. And then it can easily given to a recipient without any immune rejection. So I just, in one slide, wanted to show you all the diseases currently they are trying clinical trials using this Wharton jelly stem cells. It ranges from blood disease to infectious disease to cancer, heart disease, connective orthopedic surgeries to injuries, and all the way to all these different. These are all very early, but it seems to be promising, and hopefully in the next couple of years, at least some of these diseases, you may be able to see some promise and efficacy. And I'm going to finish up with this last one clinical trial that has used Wharton jelly stem cells. Seems to make a difference. So, I mean, both Kuhn and Willem are transplanters, bone marrow transplant physicians. So we use cord blood as a source for transplanting their patients, but one of the drawbacks of using cord blood for stem cell reconstitution is the engraftment of the stem cells takes a long time. Typically, we use G-mobilized peripheral blood stem cells or bone marrow. Within 11 to 14 days, it's completely engrafted, and a patient has a new immune system. But in terms of if you use cord blood, it takes 21, 22, sometimes 28 days. So this is a big issue without an immune system for that long. So this trial actually, let's see, used 20 patients. This is again preliminary, but it really shows that mixing Wharton jelly stem cells can really solve this problem of a bridge, creating a bridge for engraftment, and essentially treated these patients, and here is the results. Typically, like I mentioned, this is standard of therapy, 21 days for engraftment. The cells that were mixed with the Wharton jelly MSC, within 12 days, you could see the engraftment. And the cell dose that was used for mixing with is not a lot of mesenchymal stem cells, a few million. Even with that, you could see an effect. So conclusion here, based on at least on this trial, which was actually published in 2013, is umbilical cord mesenchymal stem cells can enhance the engraftment of the CD34 cells along with after a cord blood transplant for further, although further studies need to be done. This really opens up a lot of other possibilities using cord blood as a source. One of its drawbacks can be addressed by using this method. And the last couple of slides is actually, like Kuhn mentioned, we were thinking of using bone marrow derived MSCs about now 15 years ago for myocardial infarction. And people had done many trials around the US, but with very little long-lasting results. But right now, using MSCs derived from umbilical cord, the Wharton jelly, it seems to actually taken another second life again, trying these new types of stem cells. And the initial results are already in. It shows intracranial delivery was safe, so directly injecting into the myocardium also significantly improved the viability of heart function, and also no immune-related issues were observed. But large-scale studies needs to be done. Many of these studies, you really need to do large-scale studies to really see the whole spectrum of adverse effect and efficacy. So in the next few years, we may see more of these types of stem cells being applied to other indications, including orthopedic surgeries and other types of injury-prone conditions. But what I really want to emphasize in the way things are done right now, the low-hanging fruit is not the best, which is using adipose tissue. Because also what's not been considered using adipose-derived MSCs is many of these patients whose adipose is removed, they already have medical conditions. Either they are diabetic, overweight, other issues. So these MSCs from these patients are not the most healthy. So using them may really kill the field, that even for the other good MSCs may not get a good fair shake if people keep using adipose because it's easy to access and get it. So, but Wharton jelly MSC seems to be one of the sources that may make a difference. And then my last slide is cancer, diabetic, autoimmune, cardiac, neural, and genetic. Many more studies can be done using these MSCs and new stem cells. And I'm going to stop right there. Thank you.
Gracias, doctora Mita. Dos preguntas tengo acá, pero antes de pasar, yo quisiera que tocar dos aspectos. Uno es el medio ambiente al que llega la célula, que es también importante, y el otro aspecto es la cantidad de células que ocupamos transferir para una adecuada respuesta. Son dos otros factores que, aparte del tipo de célula, intervienen en esto. ¿Cómo manejar esa situación? En trasplante más o menos lo tenemos definido. Sabemos cuántas células hay que trasplantar para tener un adecuado recuperación hematológica. Pero a nivel de las otras terapias, doctora Mita.
Actually, it's very, very true. One of the you bring out very, very good points. And in terms of the cell dose, many of the phase 1, phase 2 clinical trials have built-in dose escalation for the number of cells that are required. So actually, I'm aware of one trial right now using MSCs for diabetic wound healing, for example, and has 3 different dose escalation studies. And this is very critical because we have no clue how many cells would be needed to get the proper results. So typically, many of these trials use a few million cells as a starting dose and then escalates to approximately 8 to 10 million cells. I mean, these are total number of cells, not per kilogram weight of the patient. And the second part of your question, what tissues, what sites to be used, that's a very, very more complicated question because we don't really know at different sites how they would behave. But in this regard, the type of studies that are being done mostly involves orthopedic surgery, and those seems to be have some effect. For example, also like avascular necrosis, for example, now people are trying this, and that seems to have a positive effect, but I'm sure there'll be other sites that would have no effect because cells have to also stay there at the location for it to have its own impact. So these are still very, very, that part is still very unknown.
Una de las preguntas que me plantean acá es ¿cuánto tiempo debemos de esperar para observar efectos positivos? En la experiencia suya, y yo sé que depende del tipo de órgano que manejemos y el tipo de célula, pero ¿nos podría dar una idea de cuánto podemos esperar para ver que el paciente o que notemos algún cambio debido a la utilización de las células?
Again, I can use the example with diabetic wound healing. Within at least the animal models and initial patients, within 2 weeks, you can begin seeing the healing process. 2 to 3 weeks, you can see the accelerated healing process. And this is the reason I'm using this example is because this is easy. You can see the wound healing. It's but the more difficult nature is, for example, cardiac function. So the problem people who are doing these types of studies are running into, to evaluate whether it's working well, you need sophisticated instrumentation to measure the function. And many of these studies don't have the access to these types of instrumentation, and including my institution, we turned down a trial because they required us to buy a special catheter to evaluate. So those are complicated to know whether it's working until sometimes a month or even later. I think in terms of like say hip surgery, orthopedic, you probably see an impact within a month. So it's not too long, but it's some depending on the site and the disease.
Pero que es sobre efectos secundarios. Sin embargo, hay toda una charla del doctor Amita que vamos a hablar sobre riesgos y efectos secundarios del uso de las células, los diferentes tipos de células. Otra pregunta es, cuando se refiere a la aplicación de las células madre derivadas de la grasa, ¿a qué estadios o evidencias de procedimientos inapropiados se refiere? No.
¿Qué estudios? Evidencia de procedimientos inapropiados. Well, yo creo que no hay ahora ninguna aplicación de células madres derivadas de la grasa que están totalmente apropiadas, que pueden hacerse afuera de un estudio clínico. So, let me say it in English again because it's easier.
That's okay.
So I don't think it's right now there's a single indication for use of stem cells from fat tissue, from adipose tissue. There may be studies ongoing, but the use of these cells outside of well-controlled studies is currently not appropriate, I believe. Would you agree with that, Anita?
Yes, with adipose, I think the biggest drawback is not medical effects, but you're just wasting your money. It's more of because all of these things cost money. So because they're not purified, the best thing that you could is you just wasted your money. So without having medical issues. But
the worst thing, just to add to that,
yeah.
The worst thing is that you could have side effects. And somebody was asking about side effects. One of my slides that there can be very severe side effects if this is used inappropriately, including blindness.
Otra pregunta es, ¿por qué las células, los stem cells derivadas de adipocitos, pareciera ser la mejor opción a nivel de adultos? ¿Es esa la mejor, vía de obtener stem cells o existen mejores?
No, I don't think the adipose is the best way but it's the easiest way. I mean, many of those procedures are done on an outpatient basis and very easy, but it's requires a lot of work to isolate the stem cells from adipose. Like I showed in that slide, it's only a minute fraction of the aspirate that's truly stem cells. That's why going into other sources of stem cells that are non-immunogenic can be more useful, like the MSCs. But of course, it requires a lot more work and a lot more being careful to have, expanded stem cells from the other sources. But adipose is the easiest. That's why people have been using it.
Una pregunta que nosotros usamos mucho en médula ósea es criopreservación. ¿Afecta esto la célula madre cuando la utilizamos para otros fines que no sean en trasplante hematopoyético? ¿Qué experiencia hay en congelar esas células y aplicarlas al año siguiente cuando la enfermedad está más avanzada, o etcétera?
That's a very, very good technical question. Actually, the cryopreservation technology has been there for like last 30, 40 years. But all our experience is mostly for clinical purposes is from blood stem cells. In terms of technology, MSCs, the biggest challenge in cryopreservation and a good preservation and a good way to thaw the cells without killing the cells is based on having single cell suspensions. So MSCs are able to reach that single cell stage, but it's not the same with some of the other stem cell types. So for example, actually, I'm going to talk to you either later today or tomorrow about islet transplantation. And that's a big problem because islets are not a single cell, it's a cluster. So you cannot cryopreserve, it loses all its potency. So, but for MSCs, right now, the technology is pretty good in terms of cryopreservation and preserving them for a long time and thawing and giving it back. If it's done properly, it can be maintained as long as the cells were prepared in a unicellular manner.
En el mismo tema del microbioma y en el mismo tema del medio ambiente, igualmente en trasplante, en hematología, utilizamos citoquinas tanto para aumentar el potencial de crecimiento de las células como su división. ¿Cómo está el tema de utilización de citoquinas en otros órganos, por ejemplo, a nivel miocárdico?
So there are studies of utilizing cytokinas, growth factors, cytokines to ameliorate repair of myocardial tissues. Again, with inconclusive results, but there's clearly a back and forth between stem cells and their environment, to a large degree is cytokine derived. So a lot of the field revolves around how do you influence the fate of the stem cell? Do you influence it by genetic programming, genetic reprogramming? Do you influence it by growing it or surrounding it by the right environment and the right cytokine milieu? So I think right now there are no specific answers to your question, what cytokine to use, what environment to utilize for various indications. But time will really provide answers to that. And this type of question will be very important in increasing the efficiency of these types of treatments.
Okay. ¿Qué experiencia tienen ustedes con los estudios que se llevan a cabo en términos de expresión proteómica, silenciamiento y expresión de genes, epigenética y no coding RNAs?
As far as genetic manipulation, I am not involved in any such studies that I can think of. Right now, RNAs are mostly used for research purposes. The other areas where we use this right now is increasingly for diagnostic purposes. For example, we try to diagnose graft versus host disease by various RNAi patterns in the peripheral blood. So getting a better diagnosis of an otherwise difficult to diagnose disease by using levels of various RNAs.
Yeah.
Actually, that's a very interesting question because this is a very, very new area using epigenetic changes for influencing medical treatment. So the good example, there's a drug called decitabine, and that seems to work by epigenetically promoting differentiation in the context of cancer and other diseases that the cells have stopped differentiating. Opposite extreme, actually about, I would say 5-7 years ago, there's a new group of enzymes that were discovered that can epigenetically modify. This is getting into science more deeper, but cytosine residues are methylated. If you were to add hydroxymethyl groups, that's compatible with activation of genes that are silenced. So they are called TET enzymes. And these enzymes are mutated in many conditions, especially in leukemia. So epigenetic modifications can really influence the type of genes that are transcribed, which can really push the cells to go to one direction versus the other. The appreciation of epigenetics is just coming into light. Actually, there's a really good example. People have looked at that were born by C-section versus vaginal delivery. Epigenetics is quite different. Blood. And what's very interesting is actually it's a Scandinavian group that followed this and looked at it. The methylation pattern is quite different in C-section babies. And after a couple of weeks, the epigenetics changed back to a baby that was born naturally.
Interesante. Hay 3 preguntas que versan sobre temas regulatorios, que las vamos a tocar el día de mañana. El doctor Amita tiene una charla que va a hablar sobre la intervención de FDA y etcétera. Pero me llamó la atención un comentario. ¿Por qué la FDA tiene que regular esto? Porque uno piensa Food and Drug Administration. ¿Y por qué FDA, preguntan, por qué FDA regula lo de terapia celular? Kun.
Yes, Amita can also give his opinion, but I strongly believe that a major function of government is to regulate these types of new medications to protect the public. And it is a bit artificial not to call this a drug. When we use these cells to treat human beings, and we use them exactly in the same fashion as we use any other drug. There's a fine line between what is a food, between what is a drug, and what is a cell. And now with CAR T cells, we talk about living cells. All of us are prone to misconduct. All of us are infallible. So all of us need to be regulated. That's just the way it is. There's a police force necessary in every country. Otherwise, we will go beyond the boundaries. Very powerful, but very early treatments. And there's a major temptation to overuse them and to use them in inappropriate fashions. So I think it's totally correct and actually necessary that they get regulated. But I do think the FDA struggles with how to do this. And as does every country. And I think that's the reason for this conference.
You know, I think Kun alluded to a lot of the reasons actually. So the clinical cell manufacturing facility that I direct is regulated by the FDA. So I should not be happy that they are regulating me. Actually, I'm very happy they're regulating me. Honestly, because more I've been in this field, I appreciate the need for regulation. Besides misuse, the biggest reason you really need to regulate is, I mean, we are all curious and scientists in our heart. So we can be biased in terms of if we find something new, we want it to work, even though we don't have bad intentions or misuse. If it's coming from my facility, I'm more enthusiastic. By having regulation, it brings us to start thinking more rationally. And also it develops standardization. I mean, there's, without standardization around the world, how can you compare and contrast what's best and what's not? And by creating a common set of rules, everybody can follow, we can compare and contrast. Are my cells as good as somebody else's? And these are all done. And I will go through in detail tomorrow. 2005, the US Congress passed an act that my facility is regulated by. The good part with the FDA is they took 4 years of taking input from people like us. They did not just write the rules overnight. We had open sessions. We could write write to them. They read every one of there were 10,000 comments. And they put in the rules together after talking to all the people that are creating these therapies. So really, most of the regulations are coming from us, actually. FDA is actually carrying out our wishes. So, I mean, I'm fully on board with the FDA regulations and other world bodies because it's truly needed. I mean, if you're going to treat patients safely, and I will go through, not right now, tomorrow, a slide, the 5 categories, aspects of a cell therapy that the FDA regulates. Why they want to regulate, there are 5 aspects of a cell that they are looking into, which all 5 makes sense, and it's rational, and it's very, very useful for the patient.
Y voy a fundir 2 preguntas en una. Es sobre la extracción de células a nivel de cordón umbilical. ¿Qué técnicas utilizan? Tanto para el GILI o tanto para las células de cordón umbilical. Si tienen algún método de preferencia.
So first I want to mention, I don't do this. In my facility, we don't isolate cord-derived MSCs, but I have watched other facilities do this. The major way that these cells are isolated is you first cut the cord into small pieces physically in a biological safety cabinet under sterile conditions. The key method for isolating single cell suspensions are enzyme digestion. It's a cocktail of different enzymes, proteases. Right now, there are few of those actually may become available in a clinical grade. So this is another example. So the FDA regulates every single reagent that touches that cell. It has to be made in a way that new things are not introduced. For example, most of these enzymes come from either pig or from bovine. So there are viruses and bacteria that has to be tested. So there are companies that make these reagents in a clinical grade with done all the PCR and react to show that none of these animal-borne materials have agents that can introduce into the human cells. And now more and more people are moving away from animal-based products being used to isolate stem cells for human. They are using more recombinant DNA technology to produce it in human cells. So many of these cells are isolated using these enzymes. And then the enzymes are washed out and then resuspended in a saline or a neutral pH, and then they are cryopreserved.
I want to add something. We also use cord blood cells for hematopoietic stem cell transplantation. And we use this for allogeneic donors most of the time. So there are public cord blood banks. Again, we are big customers of the banks. They get their cord bloods from mothers delivering in public hospitals, including in our hospital. There's a major bottleneck there, or a major hurdle, in which for every 10 cords they collect, from birth that the mother gives away and where they collect just the blood from the cord, they really utilize and cryopreserve only 1 or 2. Because in many cases, the numbers are small. In other cases, the mother has a health problem. The mother has been exposed to viruses. So there's a very stringent process of selecting the cords for public use. That process does not get used in the private cord blood banks when people collect their cords for their own supposedly later use. And there's a big question surrounding that, because very few of these cords selected for later public use, let's say for treating one's wrinkles 50 years down the line, with the cord, the umbilical cord from when I was born, nobody knows how well these cords will work. Nobody knows the quality of these cords in many cases of the private clinics.
Yeah, the national average of all the cord bloods that are collected by all the mothers in a public cord blood bank ultimately reaches the bank for distribution is around low 30%. 70% of all the cord blood collected from a hospital for bank do not reach the standard that's required to be sold or to be used as a transplant material. On the other hand, the private cord blood banks, if you want to save your own baby's cord blood for your own family's use, it's a commercial transaction. Many of the banks call the family saying, we got very few cells. They are not really good. Do you want us to save it? Most mothers, most families say yes. So it can be as high as 90. But like Kuhn said, their usefulness may not be, there at all. I mean, you're just paying them money just to keep your cells with very little potential use. So the standards are quite different.
Muchas gracias a los dos, con doctora Amita. Gracias. Volvemos en 20 minutos y pasamos al coffee break que está al lado. Muchas gracias.
Oh, the translator worked very well. Yeah, very good. Okay. I was nervous about this language barrier.
Yeah.
No, it's very good.
Okay.
Nice to meet you, Maria Leon. Nice to have you here. Nice to meet you. Great talks. Thank you very much.
Thank you. Coffee.
Wendy sent hi to both of you. I sent a picture. Yeah.
¿Tu nombre es? Estefan. Las computadoras y todo ellos. Hay que bajarlos ahí. Ahora recogamos los celular seguro mientras tanto sale.
O le puedo decir a Ismael que cierre la...
Ah, sí, ahorita podemos
No sé, sí, está sobre la jugada.
Sí,
Claro que sí,
claro
con
que
mucho
sí,
gusto.
doctor.
Que alguien se lo juegue.
Sí, claro.
Mucho gusto, sí, señor. ¿Todo bien, va?
Sí, todo bien. Sí, está bien. Es que yo voy a... Es que ponerle pausa, porque si no se está, es con... Ah, bueno. No, no, pero después, sí se escuchó bien, sí. Sí, fíjense que apagaron el teléfono. Oye,
Hay que dar eso ya con batería
pero
nueva.
por
Pues,
eso,
cualquier cosa así se
¿y
gasta.
esos otros tienen baterías?
Sí, sí.
Es que me pasó que tenían.
Es que como ahora estos son de baterías recargables, hay que esperar a que se...
Sí, pero... Entonces están apagados. Bueno, ellos son los mismos exponentes, entonces, ahora bueno, ellos siguen con esta charla. Vea, aquí está el programa, vean.
Que siguen
Bueno,
usando...
sigue la doctora María Rodríguez.
Y la pone aquí.
Ajá, ella la pone aquí, luego el doctor Bendice otra vez y luego el doctor Amita otra vez.
Al día.
Si es que esas computadoras no se pueden quedar.
No, no, yo me quedo aquí. Si yo veo que salen todos o pedir que salgan a todos.
Entonces, ¿qué era que dice? Yo quiero llamar a la comunidad de la casa y a ver si ya alguna.
No, no, yo me quedo aquí.
Cualquier cosa lo que hace es, si usted se queda aquí, entonces cuando ya pasan otra vez y está todo, usted va a ir. Y dale también.
Oiga, si está bien. Es que yo lo siento caliente porque ya ahorita hace mediodía yo voy a bajarlo.
Está en 22. Dejémoslo así, también.
Sí, porque
Ponemos en 20. ¿En cuánto lo pone usted?
es que yo siempre lo dejo en 20 por lo mismo.
Pero ahora en la mañana estaba muy frío.
Ah, sí, porque es que
¿Y en qué estaban? ¿En 20? ¿No?
muy caliente.
Dejémoslo así, si ellos me dicen yo le digo, porque es que eso me llama que estaba muy frío.
Bueno, es que también...
Bueno, yo voy a ir a coordinar allá, hay que a la cámara y eso, y estoy hecho un ojito y ahora cuando yo veo, casi siempre 30, pero esperamos 200, 220. No, no, más de
Y es un mantequilla, o sea, que a ver si...
supuestamente lo van a decir, doña Ley me está averiguando.
Es que si no usan expresidentes como está esa cuestión de ley, hay que desmontarlo. Hay una reunión como a las 3 y una compañera ahí. Bueno, el punto es que hay que quitar el montaje, porque ya oso otro montaje, obviamente. Pero el detalle es con los manteles, los foros de las sillas y todo. Porque
Es que no sé cuánto estamos pagando, está la 1 y 2, para cuánta gente cae.
ahí hay 120.
Sí, es que yo creo
Claro,
que,
porque
yo creo que va a quedar para los 2 días, ¿no?
o dejar, digamos, tal vez yo puedo dejar 20, 30 así, expresidente, y le hago el montaje a la compañera así. Sí. Ya, por si agarran. Entonces quedan así, yo le digo, oye, compañerita, no le puedo parece un metro, lo dejo 40 en el presidente. Cena de elección académica, delicadilla. Ah, sí. Entonces yo le digo así, 40 los presidentes, pero si se le viene gente, no se vea feo. Yo le quito.
Porque a mí me han hecho eso, cuando me dicen, es que no se lo pones pesado, que no,
Ella lo que...
y no, explíquele eso, y dígale
No,
que
yo
si
le
no,
hago unas cuatro
y si no, pues,
y le hago el agua ahí, no, pero no lo solo.
si no, dije que cuando te la
Pero esas 4 minutos ahí.
digo, es que la noche no. Es más, yo voy a confirmar con usted.
Pero sí, yo dejo así 4:40 ahí. Pero una más mañana, por lo menos no sé. Ya. Ya se quitó. Ya se quitó.
Hay que ir llamando a la gente de... ¿Ah? ¿Se está, doctora? ¿Qué?
Está apenas como...
Sí, claro. Bueno, los dos. ¿Los dos? Qué belleza. Oh, qué lindo.
Ok, vamos a ver si corre.
¿Vas a llamar?
Para ver un toquecito.
Ajá.
Así antes de... Como
Sí,
nada
o
más
si
para
quiere
ir una
la
repasada.
hacemos muy grande. Desde el
Nada más
principio.
para... Exacto.
Ok. Ok, aquí y ahí. La puede pasar de aquí o de ahí, como usted guste.
Ok, nada más para verlo, todavía no sale, ¿verdad?
No.
La saco de esta vuelta.
Vamos a revisar. Sí, lo copié aquí. Ahora, si usted quiere señalar, es con el del centro, el verde, y aquí pasa, o si usted quiere lo maneja aquí, como guste.
Y si hablo aquí más fácil.
Sí, si quiere señalar nada más estripa el verde y está el láser. Y voy a dejarla abierta. Ella, ella, María Rodríguez.
Yeah, I saw you last time on the beach. Really con el doctor Luján.
Con vasito, solo la botella. Sí, con eso.
Bueno, bienvenidos a la segunda sesión de esta mañana. Paso a presentar a nuestra primera ponente, la doctora María